In late 2025, a satellite the size of a suitcase powered up a graphics chip in orbit and did something no computer had ever done in space. It trained an artificial intelligence on the complete works of Shakespeare, then answered questions from a language model hundreds of kilometers above your head. On paper, this makes no sense. In orbit, computing costs several times more than in a warehouse in Texas. Radiation slowly kills the chips. You can't send a technician to swap a broken part, and getting rid of heat becomes a nightmare. So why would the richest companies on Earth want their most valuable machines up there? Because in the span of a single year, they all placed their bets. SpaceX, Google, Amazon's Blue Origin, Nvidia. Each one filed plans, launched hardware, or unveiled satellites built for a single purpose, running artificial intelligence in space. This is not science fiction anymore. It is a land grab. And the reason behind it is not the one you would expect. It isn't cheaper power, and it isn't free sunlight, though both matter. The real force pushing computers off the planet is something far more boring and far more unstoppable. By the end, you'll see why the hardest problem in space isn't the cold, it's the heat. To understand why, forget space for a moment and look at the ground. The artificial intelligence boom has a dirty secret. The thing holding it back is no longer clever software or even the chips themselves. It is electricity, and specifically, the aging power grid that is supposed to deliver it. A single modern AI data center can now demand as much power as a small city, 1 to 4 gigawatts each. But you cannot just plug that in. In markets like Northern Virginia, the waiting line to connect to the grid runs 4 to 7 years. The giant transformers you need take about 5 years to build. The numbers are staggering. Analysts expect data centers worldwide to swallow around 1,000 terawatt-hours of electricity this year, roughly what all of Japan uses. In the United States alone, forecasters warn of a power shortfall near 50 gigawatts by 2028. Demand is sprinting. The grid is crawling. Here's the twist that changes everything. The companies building these systems are not short on money. They have more capital than they know how to spend. What they cannot buy is time. A campus that joined the queue this spring may not receive power until 2030. Money is not the constraint. The wall socket is. And you cannot bribe your way to the front of a grid queue. There is no premium package for a new high-voltage substation. No express lane for a transformer factory. When the bottleneck is physical infrastructure that takes half a decade to build, even a trillion-dollar company has to stand in line, unless it finds a line that doesn't exist yet. That missing line is in orbit, above the atmosphere. The case for computing in space starts with the one resource Earth rations and space gives away for free: sunlight, an almost unlimited supply, falling on your solar panels every second of every day. In the right orbit, a solar panel can be up to 8 times more productive than the same panel on the ground. There are no clouds to dim it, no atmosphere to filter it, and, in a carefully chosen orbit, barely any night at all. The sun simply never sets on your data center. That continuous power is a bigger deal than it sounds. On Earth, solar farms need enormous banks of batteries to survive the night, and those batteries are heavy, costly, and wear out. In orbit, near constant sunlight means you can shrink or skip the batteries entirely and run your machines flat out around the clock. But the deepest advantage isn't the sunlight. It's that there is no queue. You cannot buy your way to the front of a grid connection, but you can buy a rocket. In space, the constraint that strangles you on the ground simply vanishes. You are trading dollars for time, and time is the one thing nobody on Earth can sell you. So the giants moved. In early 2026, SpaceX filed to launch as many as 1 million solar-powered data center satellites, then unveiled its first, a supercomputer with a wingspan wider than a Boeing 747. Google's Project Suncatcher aims to fly its custom AI chips in orbit by 2027. They aren't alone. Nvidia announced hardware built specifically for orbital data centers. Blue Origin filed for a constellation of more than 50,000 compute satellites. A startup called StarCloud is scaling toward 88,000. What made all of this suddenly thinkable was one quiet revolution: reusable rockets dragging the cost of reaching orbit down year after year. And this is where the story turns, because there is a catch that almost everyone gets backwards. Ask most people about computers in space, and they'll say cooling must be easy. Space is freezing, after all. That intuition is not just wrong, it is exactly backwards. Space is cold, but it is also empty. On Earth, you dump a computer's heat into air or water that carries it away by contact. In the vacuum of space, there is no air and no water, nothing to touch your machine, nothing to carry the heat off. A vacuum is one of the best insulators there is. There is only one way left to shed heat in a vacuum. You have to radiate it, glowing it away as invisible infrared light, the way a hot stove warms a room across empty air. And radiating heat this way is agonizingly slow compared to the cold liquid we pour over AI chips on the ground. How slow? A large radiator panel in space, held at a comfortable room temperature, sheds only around 600 watts per square meter. That is more than 1,000 times slower than the liquid cooling wrapped around a single modern AI chip. To cool a real data center, you would need radiators of almost unimaginable size. The math is brutal. To cool a single megawatt of computing in orbit, the radiators alone could weigh around 100 tons, while the computers themselves weigh perhaps 10. The cooling fins can outweigh the entire supercomputer they serve, 10 to 1. In space, you are not launching a data center. You are launching a radiator with a computer bolted on. This is why SpaceX's first orbital machine carries a liquid radiator over 100 square meters wide, quietly bleeding its heat into the dark as infrared light. The glamorous part is the AI. The hard part, the part that decides whether any of this works, is the plumbing that keeps it from cooking itself alive. Heat is the first enemy. The second is invisible, and it never stops. Beyond the shelter of Earth's atmosphere, a steady rain of high-energy particles pours through everything, including the delicate silicon that artificial intelligence depends on. Radiation flips bits, corrupts memory, and slowly degrades the chips. And you can't just call a repairman. When a chip fails in a warehouse in Texas, someone walks over and swaps it in minutes. When a chip fails 400 kilometers up, it may simply stay broken. Engineers already expect to replace the processors every 5 or 6 years, an entire fleet aging in a place no hand can reach. Yet, there is a reason for cautious hope. When Google blasted its newest AI chips with radiation inside a particle accelerator, simulating years in orbit, the chips survived without damage. It is a small result, but it hints that the silicon might just be tough enough to live where it was never meant to go. So we have unlimited power fighting impossible cooling, and tough chips fighting relentless radiation. When you add it all up, the entire dream comes down to a single number, one price that quietly decides whether orbital computing is genius or fantasy. That number is the cost of launch, measured in dollars per kilogram to low orbit. A detailed study concluded that space data centers only become cheaper than the ones on the ground once launch costs fall to roughly $200 per kilogram, a threshold we might not cross until around 2035. Today, orbital compute still costs about 4 times its earthly twin. 4 times more expensive should end the conversation. But it hasn't, because that gap is closing faster than the skeptics predicted, and because the people writing the checks aren't paying for today's price. They are buying a position in a market where the cost of reaching orbit only ever falls, and where the hunger for compute only ever climbs. Which brings us back to the machine that shouldn't exist, the little satellite reciting Shakespeare over your head. Now you can see it for what it really was. Not a stunt, and not an escape from Earth. It was a scout, sent ahead to a place where the one thing you can't build on the ground is suddenly free, room to grow. Because this was never really about sunlight, or even about space. It is about a collision between two curves, an explosion in demand for artificial intelligence, and a power grid that cannot be built fast enough to feed it. When the ground runs out of room, capital goes looking for the next empty frontier, and orbit is the emptiest frontier there is. And here is the final twist. The winner of this trillion-dollar contest will not be whoever captures the most sunlight. Sunlight up there is easy. The winner will be whoever solves the unglamorous problem nobody expected, how to throw heat away into a universe that refuses to take it. In space, the future belongs to whoever can stay cool. It may still fail. The radiators may prove too heavy, the radiation too cruel, the launch costs too stubborn. But for the first time, serious companies are spending serious money to find out, because the alternative, waiting 7 years for a wall socket on Earth, has quietly become the riskier bet. The suitcase-sized computer already ran a mine in orbit and lived to tell the tale. The only question left is how big that machine gets and how soon. The climb to the top of the world has become a climb to leave it, and the starting gun has already fired.